Hi, I am Sanjay Patel. In today's lecture, we are going to study the concept of ideals. You know group, subgroups and normal subgroups. The concept of ideal is similar to the concept of normal subgroup. That we'll see how it is similar in our later lectures. In this lecture, I am going to first introduce what is an ideal in a ring, and then we'll see some examples of ideals in this lecture. So let us begin with some definitions. So first we start with a ring. Let R plus dot be a ring and capital I is a subset of R and it is non-empty set. So I is any non-empty subset of R. Then we define the three things. The first one is called definition of left ideal. So we define three things here: left ideal, right ideal, and then finally ideal. So if the set I, which we have taken here, if the set I is a subgroup of the group R plus, if I comma plus is a subgroup of the group R with respect to the operation of addition. You know R is a ring, and with these two operations of addition and multiplication, and we also know from the definition of ring that R is an abelian group with respect to addition. So what do we want is this set I must be a subgroup of R plus. And secondly, and number two is for every element small r belongs to capital R, that is every element R in the ring, and for every x belongs to this given set I, we must have this implies R into x belongs to I. So if you take any element in the ring and any element in the given set I, then this product where R, the ring element, is on the left hand side of this multiplication sign, that is important. Then in this case, we say that I is a left ideal of the ring. So I can say I is said to be a left ideal. Is said to be a left ideal of the ring R. So this is our definition of left ideal. The left in the sense that is ring element R is multiplied on the left hand side of this multiplication sign. In the same way we define what is called right ideal. There is only one change. The definition of right ideal. Okay. So it is the same thing, just there is one change. So I am just copying this. It's not this much. So the definition of right ideal is similar. Yes. Fine. If I plus is a subgroup of R plus, so first condition is same, and the second condition there is only one change, and it is here. So for every R belongs to R and for every X belongs to I, we must have X into R belongs to I. Remember, here it is R into X and here it is X into R. So the ring element is multiplied on the right hand side of this multiplication sign. Remember, X and R are arbitrary elements. Okay, if this is the case, then this I is said to be a right ideal of the ring R is said to be a right ideal. Let me is said to be a right ideal. Okay, and finally, if an ideal is both, if a set I is satisfying both the conditions, this condition as well as this condition, then it is said to be an ideal, simply ideal or two-sided ideal. So that is our third definition. So let me write the third thing, definition of ideal. Okay, so it goes like this. Again, I will just paste that thing and modify only few things in these conditions. So first thing I want is this. Okay, so for a set I, if I plus is a subgroup of R and for every R belongs to R and every X belongs to R, we have Rx belongs to I and X into R also belongs to I. So the second condition of both the definitions 1 and 2 must be satisfied. Then this is said to be an ideal of the ring R. So in this case, the set I is said to be an ideal. Okay, so let us understand all the three. I is a non-entry subset of R. If I is a subgroup of the group R plus, okay, you know how to prove a set is subgroup. So for proving the first condition, you know that thing. Let me explain the meaning of a subgroup. We know H is a subgroup of a group G comma star. Okay, if and only if for every A and B belongs to H, you know that A star B inverse belongs to H. But in our case, the operation is plus here. So I will write this thing as A minus B belongs to H. And my H is the set I. So if you want to prove that I is a subgroup of R plus, what you need to prove is this, that for every A and B belongs to I, we must have A minus B belongs to I. Okay, to prove that I is a subgroup of the group R with respect to addition. So keep in mind that for the first statement, first condition, that I plus is a subgroup of R plus, you need to prove this condition. Okay, and the second condition is simple. So if I is an ideal, it is also called simply an ideal, means the left ideal as well as the right ideal. Then it is called ideal or simply two-sided ideal. Okay, so I can also define this in a different way. Let me write this way. If I is both left ideal and right ideal then I is said to be an ideal or two-sided ideal. It is called two-sided ideal of the ring R. So this is another way of defining ideal. Okay. One thing you can note immediately is that in a commutative ring, a left ideal is always a right ideal. If some set is a left ideal, it is automatically a right ideal, because commutative means A into B is same as B into A. Multiplication operation is commutative. So let me just make a simple remark. Note that if capital R is commutative ring, then a left ideal, every left ideal is also a right ideal, and vice versa. So a right ideal is also left ideal, and left ideal is always a right ideal in a commutative ring. Remember. So if you have a commutative ring, and if you are asked to prove a set is an ideal, you need to prove only it is a left ideal. Okay. So keeping in mind all this, let us start with some examples. So examples of ideals. So let me take some example from the ring of matrices. So the first example I am taking here is this. Let M2 cross 2 R comma plus comma dot be the ring of matrices, ring of 2 cross 2 matrices. So it contains all 2 by 2 matrices, and operations plus and dot are the usual addition of matrices and multiplication of matrices. Consider a set, some set I am taking in this set of matrices as set I is equal to say A0 B0. So I am collecting all those matrices for which the second column is 0. The first column can be anything. So here A and B are any two real numbers. Just note that for real number system, we are going to use the symbol script R, and for the ring, simple R. Okay, and the problem is prove that this I is a left ideal in the given ring in M2 cross 2 R, but it is not a right ideal. So if someone asks you what is the example of a set which is left ideal but not a right ideal, then you can give this example. There can be many also. First of all, let us prove that this is a left ideal. So to prove something is a left ideal or right ideal, the first thing you should prove is it is a subgroup and it is a non-empty set. So as the element say 1, 2, 0, 0. So this I contains all such matrices. So this kind of matrix belongs to the set I can say that I is a non-empty set. So that is first thing. Okay. Now to prove I is a subgroup of this M2 cross 2, what should I do is, let us take any two elements from the set I. Our set I is this set. So I am taking two arbitrary elements. Say let say A and B. A is equal to say A B 0 0 and B is equal to say P Q 0 0 belongs to the set I. So I am taking any two matrices from the set I. One matrix I am denoting by capital A, other is by capital B. So it can be written in this form. What should I prove is A minus B. You know, whenever AB belongs to I, you should prove A minus B belongs to I. That we have already understood here. Let me show you again. Yes, we have already discussed this. To prove that I is a subgroup of R plus, just show that AB belongs to I implies A minus B belongs to I. So I am taking two matrices A and B, and I will show now that A minus B, if you take A minus B, you know it is very simple. Just taking the subtraction, you will get A minus B, B minus Q, 0 minus 0 is 0, 0. Okay. So this is also of the form, you can say X, Y, 0, 0. Okay. So this belongs to the set I. This belongs to the set I because this matrix is also of the form X, 0, Y, 0, where X is equal to A minus P and Y is equal to B minus Q. Okay. So what I have proved is for every AB belongs to I, A minus B also belongs to I. So that is my second condition. So let me write that for every A and B belongs to I implies A minus B belongs to I. So this is my second condition. Now for the next condition, the third condition, we take one element from the ring and one element from the given set I. What is our ring? Our ring is ring of matrices, which is of order 2. So let us take one element, say that I will denote it by, say, capital A is equal to, say, A, B, or let me write some other notation. A is equal to PQRS. Okay, PQRS belong to the ring R. What is the ring R? Ring R is M2 cross 2 R. So in the ring of matrices, I am taking an arbitrary element and I am taking another element which I will denote by capital X from the set I. What is our set I? Our set I is this set which contains matrices of the form AB 0 0. The first column is AB, second column is 0 0. So I am taking an arbitrary matrix from the set I. So I will write it like this. Let X is equal to AB 0 0 belongs to capital I. After taking one element from the ring and one element from the given set I, if you want to prove it is a left ideal, just multiply this ring element, that is capital A in this case, on the left hand side of the element of the set I. That means we consider, let me write this way, then if I write, say, the ring element on the left hand side of multiplication sign, just recall the condition of the left ideal ring, and the condition is this: for every R belongs to R and for every X belongs to I, we must have, say, R into X belongs to I. This is our condition of left ideal. Okay, R into X. Here instead of R, I have taken capital A, this element of the ring. So A into X, that is PQRS multiplied by the element A0, B0, like this. Now if you multiply these two, what you will get is this is equal to, you know how to multiply two matrices. The first row is kept fixed. It is multiplied with this first column. So P into A plus Q into B. Then this row is multiplied with this second column. So P into 0 plus Q into 0. So it is 0. Then for the second row here, we consider this second row of the first matrix and multiply with each of this column, this and then this. So RA plus S into B, and then this will be definitely 0 as the second column is 0. So this is again of the form, if you write it like this, say A dash, B dash, 0, 0, where A dash is nothing but P into A plus Q into B. Just I am labeling this number PA plus QB as A dash and the second number as B dash, and that is RA plus SB, and both are nothing but both are real numbers. So both are reals. So A into X, this matrix is of the form A dash 0, B dash 0. But such matrices belongs to the set I. So what we have proved? We have proved that if we take anything from the ring R and anything from the set I and multiply in this order A into X, then you will get the resultant matrix or result in the set I. So let me rewrite that. Thus, for every, say, A belongs to the ring R and for every X belongs to I have proved that A into X, this belongs to I. Okay, so this is our third condition. So from 1, 2 and 3, it follows that I is a left ideal. Okay, so from 1, 2 and 3, it follows that capital I is a left ideal, is a left ideal of the ring R, which is nothing but the ring of matrices. Let me write like this also. Of the ring R is equal to M2 cross 2 R. Okay. But this I is a left ideal, but it is not a right ideal, which is asked in our problem. You can see here, prove that I is the left ideal in the ring R, that is M2 cross 2 of R, but it is not a right ideal. So let us concentrate how to prove it is not a right ideal. What is the condition for right ideal? Let us recall that condition. You know, to prove right ideal, what you have to do is for every R belongs to R and for every X belongs to I, we must prove that X into R, that ring element must be written on the right hand side of this multiplication sign, and that resultant element must belong to I. If this is the case, then it is called right ideal. So this is known to us from our definition. Just I am rewriting to give you a reference. Now to show that this is not true, because you want to prove that a given set I is not a right ideal, I will be taking the same two elements, because the first condition is already there. You know what is the right ideal definition. Second condition, I will be proving that it is not true. So I will consider the same A and X, and instead of A into X, now I should consider X into A for checking the right ideal condition. So let us consider X into A. For say A is equal to PQRS, and this belongs to the ring R, and or belongs to M2 cross 2. R means M2 cross 2 ring of matrices, and say X is equal to AB0, which belongs to I, the given set. We have, if I multiply these two in this order, the ring element I want to write now on the right hand side. So X into A. This A is the element of the ring R, while X is the element of the set I. So for right ideal, write the element of ring on the right hand side of the dot, that is multiplication sign. So X into A. X is AB00 and into this PQRS. Okay. So if you multiply these two, what you are going to get is this is equal to A into P plus 0 into R. So it is A into P. Then A into Q plus 0 into S. So it is AQ. Then B into P plus 0 into R. So BP plus B into Q plus 0 into S. So it is BQ. Okay. Now note that this matrix need is not always of the form A, B, yeah, like this, A, B, 0, 0. If these numbers are not 0, and that may happen if I take A not equal to 0, B not equal to 0, and Q not equal to 0, then this does not belong to I. If A and B and Q are not equal to 0. Okay. So that suggests that the set I is not a right ideal. To be more precise, I can take one simple example to explain this, why it is not so. For example, if we choose any element from the ring of matrices, say like this, 1, 2, 0, 0, okay, that is X, this belongs to I. And if I take say a matrix A is equal to say 0, 0, and say 2 and 3, let me write like this, or I can take anything, not necessarily I want to take PQRS. Let me choose some nice numbers so that you will not be confused. So let me take like this, some element from the ring R. So it is M2 cross 2 of R. And if you multiply in this manner X into A, what you are going to get is 1, 2, 0, 0 into 0, 1, 2, 3. Let us multiply these two. So 1 into 0 plus 0 into 1, that is 0. Okay. Then 1 into 2 plus 0 into 3, so it is 2. 2 into 0 plus 0 into 1, so this is 0. Then 2 into 2, that is 4, plus 0, so this is 4. Okay. And it is clearly not a member of I. Okay. So this is a particular case. You can also give this reason why I is not a right ideal. So I can say therefore capital I is not a right ideal. He is not a right ideal. So this is an example, very important example of a set which is a left ideal but not a right ideal. What is that example? Let us recall the set of all matrices of the form A, B, 0, 0. The first column is A, B, and second column is 0, 0. It is a left ideal, but it is not a right ideal. So this is a left ideal, but not a right ideal. Okay. Let us take another example of say set which is right ideal but not a left ideal. Okay. So let me put it here. Okay. And let us change this. I am taking the second example in the same ring of matrices of order 2, and I am changing these things. I am taking the set I instead of this kind of matrices. What I want to take here is, just a minute, this I will change. I will consider matrices of the form A, B, 0, 0. So the first row is A, B and second row is always 0. Then prove that this set I is a right ideal but not a left ideal. So this is an example of a set which is a right ideal but not a left ideal. Okay. A very important example again. Okay. The proof goes in a similar way. Just I will prove the main things. First of all, note that it is a non-empty set. So clear the element 1, 2, 0, 0. This belongs to I because I contains all such matrices. It indicates that I is a non-empty set. So this is my first result. Second thing is I want to prove that I is a subgroup of R plus. So let me take two elements, that A is equal to A1, B1, 0, 0 and B is equal to A2, B2, 0, 0. Both belongs to I. And then you can easily verify that A minus B is A1 minus A2 and B1 minus B2, 0, 0. You can use any symbols. This is simple, so I am writing like this. So this matrix is of the form A, B, 0, 0. I am calling this A1 minus A2 as A and B1 minus B2 as B. So where A is equal to A1 minus A2 and B is equal to B1 minus B2, and these are real numbers. So this belongs to, again, the set I. This belongs to I. So what I have proved here is, if you take AB belongs to I, then A minus B belongs to I. So therefore, for every A and B belongs to I implies A minus B belongs to I. This means I is a subgroup of R plus. The last condition is the ideal condition, I will say. So we'll take one element from the ring R and one element from the set I. So let me choose, say, capital A is equal to, say, PQRS, and that is in the ring R, which is nothing but M2 cross 2 matrices, and one element X. Now our set I contains all those matrices where the first row can be anything, but second row is always 0. So I'm taking A, B, 0, 0. Okay, this belongs to I. B, any two elements. So these two are arbitrary. Arbitrary means any two elements in this sets. To prove it is right ideal, what should I do is, I should multiply the element A, which is in the ring R, on the right hand side of the multiplication sign. So then if I consider, then this X into A. So I'm multiplying this element A, which is from the ring R, on the right hand side of this X, that is right hand side of this dot. So X is AB00 dot PQRS. If you multiply these two, what you will get is A into P, okay, plus B into R. So AP plus BR, that is the first element, then A into Q plus B into S. So AQ plus BS. Then 0 into P, 0 into S. So this second row is 0. So if you multiply with all this, you will get 0 and 0 over here. So this is of the form. This is of the form, say, A. Let me use some other A dash, B dash, 0, 0. Okay, where A dash is this element and B dash is this element. So what is proved? That this X into A is of the form A dash, B dash, 0, 0, and therefore it belongs to I. So for every A belongs to R and for every X belongs to I, because A and X are arbitrary, I can say that for every, say, A belongs to R and for every X belongs to I, we have X into A belongs to I. This is my third result. So from 1, 2 and 3, from 1, 2 and 3, it follows that capital I is a right ideal. Capital I is a right ideal in the ring R. Okay. But we also want to show that it is not a left ideal. So for left ideal, only one thing is left, that we should check the condition of left ideal. Say, let me take one special case directly. Let some matrix from the ring say R, which is set of all 2 cross 2 matrices. So let us take A is equal to 1, 2, 3, 4. Okay, this belongs to the ring R. Before we check, because we know the answer, we are asked to prove it is not a right ideal. So I am taking one element from the ring R and one element X from the set I, which is a left ideal, is already proved. So that element, the first row I can take, say 1, 2, second row 0, 0. You can take anything. Let me take, say 4, 5 in order to avoid the confusion. Say this is 4, 5 and this belongs to I. Okay. Then if I multiply this ring element on the left hand side of dot sign, that is if I consider A into X, A means 1, 2, 3, 4 and X is 4, 5, 0, 0. If I multiply these two, what I will get here is 1 into 4 plus 2 into 0. So 4, 1 into 5 plus 2 into 0. So that is 5 and 1 into 4. 1 into 4 plus 2 into 0. And 1 into 5 plus 2 into 0, it is fine. Then 3 into 4, that is 12. Plus 4 into 0, so 12 only, and 3 into 5 plus 0 into 4, so it is 15. Okay, and it is clear that this is not an element in the set I, because our I contains matrices which are of the form this. You can see that example A, B, 0, 0, and this matrix is not of the form A, B, 0, 0. So therefore I can say that I is not a left ideal. Why it is not a left ideal? Because this A ring element is on the left hand side of A, and for this particular matrices we have shown that A into X does not belong to I. So that ideal condition, the left ideal condition fails. So this is an example of a set which is a right ideal but not a left ideal. Let me take another example in the same ring. Say number 3. So I will write in short, let R is equal to the ring of matrices. So now onwards I will write in short form, ring of matrices, and let us take I is equal to the set of matrices of the form A0, 0B, that is set of all diagonal matrices where A and B are real numbers. Okay, then prove that I is neither left ideal nor a right ideal. Okay, let us prove. That can be proved directly also by taking or trying some particular elements from the ring and from the given set. Remember, our I contains all this kind of matrices. Okay, and you know what is the definition of an ideal? It must be a subgroup of the group R plus. So I am not checking that condition, but can check the conditions in any order. What I will do here is I will check only the ideal condition. So first part, let me consider the first that this is not a left ideal. So let us take one element, say A is equal to PQRS. Okay. Or let me take some particular values instead of general case. That will be easier for you to understand. So I'm taking one element 1, 2, 3, 4, say belongs to the ring R, which is M2 cross 2, set of all 2 cross 2 matrices. And I'm taking one element, say capital X, from the given set I, which is set of all diagonal matrices. So I'm taking a matrix like this, 1, 0, 0, 2 belongs to I. Now let us try to multiply this. Let me remove this. So first, what I will do here is consider, say, A into X. So remember that this A, which is the element of the ring R, is multiplied on the left hand side of this dot. So A into X means 1, 2, 3, 4 into, say, 1, 0, 0, 2. So this is equal to, say 1 into 1 plus 2 into 0, so 1. Then 1 into 0 plus 2 into 2, that is 4. Then 3 into 1 plus 4 into 0, so 3. Then 3 into 0 plus 4 into 2, that is 8. So A belongs to R, X belongs to I, but A into X we are getting this matrix, which is not a diagonal matrix. So this is not a member of the set I, because I contains the set of all 2 cross 2 diagonal matrices. So thus we have A belongs to R and X belongs to I, but A into X does not belong to I. You can prove in a general form also, but we are taking this particular case to understand easily. Now consider, let me write the conclusion first. This means that this I is not a, this means I is not a left ideal, is not a left ideal, because that left ideal condition is not satisfied. So this is my first result. Now I will show that it is also not a right ideal. So what should I do is consider, say, X into A. I will be taking the same X. X is the element of the ring, which I have taken as 1, 0, 0, 2, 1, 0, 0, 2, and A is 1, 2, 3, 4. If you multiply these two, what you will get is 1 into 1 plus 0 into 3, 1 into 2, then 0 and 2 into 3 is 6, and 0 into 2 and 2 into 4 is 8. So we will get this matrix multiplication, which is clearly not in I, because I contains only diagonal matrices. So these two elements are not 0. So what we have proved is, for this above, A belongs to R and X belongs to I, but X into A does not belong to I, which means this set I, the set I is not a right ideal, is not a right ideal. So from A and B it follows that the set I is neither a left ideal nor a right ideal. So again, a very important example. Okay. So we're taking these examples in the ring of matrices. Okay. and shown that how to prove a set is left ideal or right ideal or not an ideal. Okay. Let me take another example of a set which is really an ideal, and let us change the ring also. So my fourth example, let us consider say z comma plus comma dot be the ring of matrices, ring of integers, and let m belongs to z be fixed. This is some fixed integer. Okay, and define the set I as the set of all multiples of m. So it is m into k, where k is any integer. So this contains, if you put k is equal to 0, 1, 2, 3, minus 1, minus 2, minus 3, what you will be getting is 0, then plus or minus m, plus or minus 2m, plus or minus 3m, and so on. So this is my set I. And I am going to prove that this set, which is a very, very important example, prove that I is an ideal in the ring Z. Okay, very, very important example. Before we prove it is an ideal, just note that the set of integers is a commutative ring with unity. We know that Z is commutative with respect to multiplication. A dot B is same as B dot A. And we have noted earlier that in a commutative ring, if you want to prove some set is an ideal, it is sufficient to prove it is either a left ideal or a right ideal. So I'll be proving that it is only a left ideal. So first note that clearly I is non-empty. I is non-empty set. This is first thing. Second thing is I have to show it is a subgroup. Let us take two elements. Let us say x and y belong to I be arbitrary. Okay. As x belongs to I, x is of the form m into k1, because all elements of I are of the form m into some integer. Okay, they are all multiples of m. So x is m into k1 and y I can take as m into k2, where what is k1 and k2? Where k1 and k2 are some integers. Now to prove that first condition of ideal, that for every xy belongs to I should show I should prove that x minus y also belongs to I. In order to show that I plus is a subgroup. So this implies x minus y, that is m into k1 minus m into k2, which is equal to, I can write it as m into k1 minus k2. And remember, k1 and k2 are integers, so k1 minus k2 is also an integer. So I can put k is equal to k1 minus k2, which belongs to z. So therefore, I can say x minus y is also of the form m into k, and hence it belongs to I. So what is proved? For every x and y belongs to I have proved that x minus y belongs to I. That means I plus is a subgroup. That is I comma plus is a subgroup of R comma plus. Our ring R is the ring of integers. So this is my second conclusion, that I is a subgroup of R plus. Now to prove the left ideal condition, let us take one element from the ring. So let R belongs to Z, which is our ring. Let me write this way so that you can understand more clearly. Let R, any element in the ring R. What is our ring R? Ring R is the set of integers. And X belongs to the set I. Okay? Be arbitrary. Then, as X belongs to I, we can write X in the form M into K, because all elements of I are nothing but multiples of M. Okay, so you can write for some K belongs to Z. So this X is also some multiple of M. I can write it as M into K. Then if I find R dot X, so I'm multiplying the ring element, that is small r, on the left hand side. Remember, R is any integer. So R into X. So R into X is M into K. Okay, because X is nothing but M into K, which I can rewrite because R, M and K all are integers here, and multiplication of integers is commutative as well as associative. So I can rearrange this and write it in the form M into, say, R into K. Okay, by rearranging the numbers. These are all integers. So this is of the form M into some integer, because M and this are all integers in this case. So this is M into, say, T, where T is equal to R into K, and that is also some integer. So this element R into X is of the form M into T. So this belongs to I. So what I have proved? If X belongs to I and R belongs to R, that is Z, then R into X belongs to I. So thus, for every R belongs to capital R, that is Z, and for every X belongs to I, we have proved that R into X belongs to I. This is my third conclusion. What is the first thing? We have shown that I is non-empty. Second thing is I plus is a subgroup of Z plus. And the third thing is it satisfies this left ideal condition. This is the left ideal condition because the ring element R, small r, is multiplied on the left hand side of this dot. So thus, from 1, 2 and 3, it follows that capital I is a left ideal of Z, left ideal of the ring Z. Okay, but since Z plus dot is commutative ring, I can say, but Z plus dot is a commutative ring. Is a commutative ring means the multiplication is commutative. We can say that I is also, therefore I is also a right ideal. In a commutative ring, remember, always every left ideal is right ideal as well as right ideal is left ideal. It is sufficient to prove only one thing. Either you prove it is a right ideal or prove that it is a left ideal. Okay, so from these two things, I is the left ideal, is one, so this, and I is a right ideal. We can say that the set I is, which is defined like this, M into K, where K belongs to Z, is an ideal of the ring Z plus dot, of the ring Z plus dot. And remember, this ideal, as you know, is also denoted by M into Z. Let me write in the new line, not here. This ideal I, which is very, very important example, this I is same as m into z. Another notation for this set. This is always an ideal. In the ring of integers, this kind of set is always an ideal. It's always an ideal in Z. Now you have many examples of ideals. 2 into Z, 3 into Z, 4 into Z. If you take any integer and consider all the multiples of that integer, it always forms an ideal in the ring of integers. So we have seen some very important examples of ideals. In the next lecture, we are going to prove one more example and then list some important thing about ideals. So till then, goodbye.